So this is lecture 6, and in last lecture we have discussed about the Laplace transform, and also we have discussed the different advantages of using Laplace transform. So today I will show you some important signals that we use in control systems, and I hope you all are aware of those signals because you have studied it in signals and networks class. So some important signals, so those are unit step, ramp, parabolic, impulse. So some important signals, so that we will be using in control systems, and they are also used as test signal. So the first one is that unit step. So unit step signals means here that ft, it is defined like this: ft equal to 1 when t greater than 0 and equal to 2 when t less than 0. So this is unit step function, and unit step is defined as ut. The other signals are that ramp signal, and it is unit ramp, so that means that slope is 1, and it is defined as ft equal to t. As it is unit ramp, so the slope is 1 when t greater equal to 0 and equal to 0 when t less than 0. And this unit ramp function is normally denoted as RT. The other standard signals what we use in control systems as well as in signals and networks, those are parabolic signal. Say parabolic signal, parabolic, it is described as ft equal to half t square when t greater equal to 0 and equal to 0 when t less than 0. And another important function what we use, that is impulse. Impulse. So impulse function, that is ft, it is described as ft equal to the delta t equal to 1, and we are talking about that unit impulse. So the magnitude is 1 when t equal to 0, and this is equal to 0 when t not equal to 0. So those things already you have studied in your signals and networks. So here just I am again discussing just for recapitulation. And this parabolic signal denoted by t, and that impulse response, it is normally that denoted by delta t. So what would be the Laplace transform of those standard signals? So Laplace transform of delta t equal to 1. You know all of those things. I am just discussing it. To recapitulate what you have studied in signals and networks, that is 1 by s, and here s is that Laplace variable. Then Laplace transform of unit ramp function, that is 1 by s square. Again the Laplace transform, so this L is that Laplace operator, Pt equal to 1 by s cube. There are some other standard signals like exponential, sine, cosine. So here I will be just writing that if you take Laplace transform of those standard signals, what are the transformed function, that is Laplace transform of e to the power exponential signal alpha t. So this alpha is the real number, that is 1 by s plus alpha. Then Laplace transform of t e to the power minus alpha t. This one is 1 by s plus alpha whole square. Similarly, that Laplace transform of sinusoidal signal with angular velocity omega t. You can have all of those transformations in signals networks books or any standard control systems books, a square plus omega square. Then that Laplace transform of cosine omega t, that is s by s square plus omega square. So now throughout this course will be handling the dynamical systems, and the dynamical systems are modeled using differential equation. So all through the course we will be taking Laplace transform of derivative operator. So what would be the Laplace transform of that derivative operator? So suppose nth order derivative function of t dtn. So it is s to the power n fs. So fs is actually the Laplace transform of that function ft. So then s n minus 1 f0, then s n minus 2 f dash 0. So here f dash is the first order derivative of that function at the value 0, t equal to 0, up to f n minus 1 order derivative evaluated at t equal to 0. So this is that formula. I hope you all know it. So we'll be applying those formulas to solve some control problems. Then what would be the Laplace transform of that integrator operator, that means 0 to t function of say tau d tau, that is fs by s. And there is one important property of Laplace transform, that means if you take the Laplace transform of two signals and the convolution of two signals, so then it would be the product of the two transformed Laplace transformed functions, that is Laplace transform of the convolution of two signals. So here f1t is a function or signal and f2t is another signal, and this star is that convolution, this star is convolution. So then that would be f1s into f2s. So this f1s is the Laplace transform of f1t and f2s is Laplace transform of f2t. So now if you introduce the delay or time shifting operator, so then what happens? It's a function of t minus capital T. So capital T is the delay, and here u is that unit step function. It is delayed by capital T. So then if you take that Laplace transform, it would be e to the power minus s capital T fs. So where fs is the Laplace transform of ft. So these are the Laplace transform of some standard functions that we will be using throughout our control systems course. And here we have some standard signals. These are the definitions. I hope you all know those things. Here I am discussing it just for recapitulation. And then one important theorem I am going to discuss, that is called that initial value theorem. Again, you have studied it in signal networks course, that is initial value theorem. Initial value theorem. So here initial value theorem means, suppose a function is given, and if you would like to find what would be the value of that function when t tends to 0, so you can have it in Laplace domain as well. So that is initial value theorem states that limit t tends to 0, function of t that is equal to limit s tends to infinity s fs, provided that the limit exists. If the limit exists. So this is that initial value theorem, and here I am not going to show the proof of this initial value theorem. If you are interested in, you can see some standard book on signals. And there is another theorem but we will be using explicitly in this course, that is that final value theorem. So final value theorem, it is just opposite to that initial value theorem. That means if you would like to find out what would be the value of that function when t tends to infinity, then it can also be obtained in Laplace domain as follows. So according to the final value theorem, we can say that when t tends to infinity, then what would be the value of ft, that is limit s tends to 0 s fs. But you cannot apply this final value theorem everywhere. So final value theorem can be applied if that function s into fs is analytic on the imaginary axis and in the right half of that s plane. So that is very important. That means if a function is given to you and if you directly blindly apply final value theorem, you will be getting a result, but that result is not correct. So for final value theorem, you need to first check whether this function sfs, whether this sfs is analytic or not. If sfs is analytic, on the imaginary axis, and in the right half of the S plane, the right half of the S plane, right half of that S plane, then you can apply final value theorem. So before applying final value theorem, you should be careful about it. You should check that one. So that means according to the final value theorem, so limit t tends to infinity, ft, this is equal to limit s tends to 0, s fs. So that means the function sfs is analytic on the imaginary axis and on the right half of that S plane, means it should not have any pole on the imaginary axis or on the right half of that S plane. That means if SFS has any pole with real part with real part 0 or positive, the final value theorem is not applicable. The final value theorem is not applicable. So this is very important. Just now we'll see some examples, and from there you will see that if you blindly apply final value theorem, so then it gives you some result, but those results are not correct. So let us see some examples. So suppose a function is given, so that is here, say one function is given, and if you take that Laplace transform of that function, so you will get that fs. So this fs is, suppose it is 5 by s into s square plus s plus 2. So then if you are interested in to see what would be the value of this function, when t tends to infinity, so then we can apply final value theorem. But before applying final value theorem, we need to see whether that SFS is analytic on the closed right half of that S plane or not. And you can see that SFS, if you do that, so you will get 5 into s square plus s plus 2. And this function is analytic because the poles are lying in the left half of that S plane. So you can apply the final value theorem, and if you apply final value theorem, what will you get? So limit t tends to infinity, ft, so this one equal to, according to final value theorem, limit s tends to 0, s fs. So sfs, what we have seen here, sfs is 5 by s square plus s plus 2. So that is limit s tends to 0, 5 by s square plus s plus 2. So then if you apply this limit, you will get 5 by 2. So let us another example. Suppose fs is given So let fs is omega by s square plus omega square, or fs you have another function. So this is f1s, this is f2s, this one equal to s plus 1 divided by s into s minus 2. So in this case, in both the cases, you can see here SFS, that means if you find that SFN, so SF1 would be S into omega divided by S square plus omega square, and in this case you have SF2, that one equal to S plus 1 divided by S minus 2. So you can see here that this particular function has two poles on the imaginary axis, plus minus j omega, and here you can see that it has a pole at 2. That means this pole lies in the right half of that S plane. So both the functions f1s and f2s, they are not analytic. That means sf1, I can write it here, sf1 and sf2 are not analytic, on the imaginary axis, since imaginary axis, and in the say SF1 is not analytic on the imaginary axis. So I think we can write it like this. Here we can say that SF1, is not analytic on the imaginary axis, and SF2 is not analytic in the right half of the S plane. So clearly the condition for applying that final value theorem is violated. So final value theorem cannot be applied. So final value theorem cannot be applied. So you should be careful before applying the final value theorem, because if you apply final value theorem, say suppose in this case your answer would be minus half. In this case the answer would be minus half, which is wrong. So you may think that, you know, if you apply a function, that is, suppose if you apply unit step, what would be the final steady state value, and if you apply final value theorem you will get minus half, and if you think that that is the correct one, no. The reason is this system is actually unstable system, so it does not have any steady state. So that's why, you know, before applying the final value theorem you should be careful about the condition which is required for the final value theorem, that is the analytic property on the imaginary axis on the right and on the right half of that S plane. So now let us take one example, and I would ask all of you to simulate this example in MATLAB, then you can see what happens. So another example, So suppose you have a system which is a pure integrator with some gain. So suppose this is k1 by s. This is a pure integrator, and you have closed that loop with a feedback gain k2. So those blocks are available in Simulink. I would ask you to simulate it and you see the response. Suppose you have used that negative feedback and you have applied that unit step. You have applied unit step here. So unit step means that US would be equal to 1 by s. Now here you have that error signal ES, and here you have that control signal YS. So here YS means if you take the Laplace transform of YT, so then you will get YS. So now you are asked to find, that means in this particular closed loop control system, if you apply that unit step function here, if you apply this unit step function here, what would be the output when t tends to infinity? Whenever t tends to infinity, what is the output? So we'll be applying final value theorem here. So let us first simplify this closed loop feedback system. So here you can see that YS equal to K1S into ES. So here that K1S, so ES is so that is K1S into ES. So ES means that is US minus K2 into YS. So here you can see that this US is 1 by S. So that means in place of US, I'll write that 1 by S. So now if you simplify that one, you will get that you just take this right hand part to the left, and then you will get that 1 plus, this is a simple algebraic equation, so 1 plus K1 K2 divided by S into YS, that is equal to K1 S square. So now what is YS? So YS is K1 S square divided by S plus K1 K2 divided by S. So now if you simplify this one, you will get K1 divided by S into S plus K1 into K2. So now we'll be applying that final value theorem. So now if you would like to apply final value theorem, so then we need to see whether SYS is analytic or not. SYS, so if you take SYS, so this one equal to K1 S plus K1 K2, and in this particular closed loop feedback control systems, we have taken that K1 and K2, they are positive. So since K1 and K2 are positive, so then from here you can see that the poles are on the left hand side of that S plane. That means this one is analytic. So this one is analytic. This one is analytic on the imaginary axis as well as on the right half of that S plane is analytic. Is analytic in the closed. So closed means it includes also the imaginary axis. Closed right half of the S plane. So that means we can apply final value theorem. So now if we apply final value theorem, what will we get? So limit t tends to infinity yt. So limit t tends to infinity yt that is, we'll get that limit s tends to 0 sys. So we are getting this relationship from that final value theorem, that is limit s tends to 0 k1 divided by s plus k1 k2, and you will get 1 by k2. So now if you take the different values of k1 and k2, so suppose k2 equal to 1. So k2 equal to 1 means here you can see that k2 equal to 1. That means feedback, if you take unity feedback, then you will get yt equal to 1 when t tends to, so t tends to infinity. That means the steady state value that you will get, that 1 equal to 1. Now if you change this k2, that means from here also you can understand what is the role of feedback in closed loop control system. So if you change this k2 equal to 0.25, then you will see that the yt, that means you know the steady state value of that control variable, it becomes 4 when t tends to infinity. So from this particular example you have learned two things. One is, you know, what are the effects of this k1 and k2, that means what is the effect of feedback in a closed loop control systems. This is one thing. And the second one, you have learned that how to find the value of the control variable when t tends to infinity. That means what is the steady state value of the control variable just by applying final value theorem. And one important thing you should note it down, that means for applying final value theorem, you need to first check whether that SFS is analytic in the closed right half of that S plane or not. If it is not analytic in that particular region, then you cannot apply final value theorem. If you apply, then you will be getting some wrong result. So now we will be discussing that inverse Laplace transform. You have studied it, inverse Laplace transform. So in this class we will be solving some problems, and from there you will just learn some few new concepts, and probably you have learned those things in your signals and networks course. So let us see what is that, how to apply that inverse Laplace transform to find that function. So where to use this inverse Laplace transform. So whenever GS is given, say GS is given, and if you ask to find GT, so then you need to take that inverse Laplace transform. That means this GT equal to inverse Laplace transform, that is the notation of GS. So we'll just learn this inverse Laplace transform via some examples. So let us take one example. So suppose one plant, or say suppose one function is given, that is GS, equal to 5s plus 3 divided by s plus 1, s plus 2, s plus 3. So your job is to find GT. So how will we be doing that? So we will be finding first that partial fractions of this function, and I hope you all have heard of that name, that Oliver Heaviside. He just gave us one method for finding that partial fraction. So here first we represent this GS. So represent this GS in partial fractional form, that is 5s plus 3 divided by s plus 1, then s plus 2, then s plus 3. So it can be represented as a by s plus 1 plus b by s plus 2 plus c by s plus 3. So then if you apply that Heaviside formula, so that means this a, it would be that s plus 1. I think you all know those things. If you forget it, I suggest you to see some standard book on signals networks, or you can see all of those things in any control book. So at s equal to 1, so that value you will get a equal to minus 1. Now b, so b is s plus 2, so s plus 2 into GS. So you find this one at s equal to minus 2, and you will get that value, this one equal to 7. Then C, so C, it would be s plus 3, so s plus 3, s plus 3 into GS, and you find it at s equal to minus 3. So then the value that you will get, that is equal to minus 6. So then you can write you can, if you just write this particular expression as a, b and c, if you write it in place of a, that is -1, 7 and -6. So this gs is equal to -1 by s plus 1, then that is equal to 7 by s plus 2, and this one equal to 6 by s plus 3. So then it is written in partial fraction form, and then directly you can just apply inverse Laplace transform, and you can use that table, or you know that formulas that we have written at the very beginning, so we can apply those things. So these formulas, then directly you can find that this gt you will get, this gt is e to the power minus t plus 7 e to the power minus 2t minus 6 e to the power minus 3t. So this is that gt, and you get this expression just applying inverse Laplace transform. So here one important concept you can have from this particular example, that this particular transfer function is given and it has 3 poles, that is at -1, -2 and -3. So in last class you have seen what would be the pole 0 map. So that means if you just draw that pole 0 map, so that is sigma, that is j omega, then the poles are at -1, -2 and -3, -1, -2 and -3, and you have one 0, finite 0, that is at -3 by 5. So if you just plot it, so -3 by 5, so you have one 0 here, so that is -3 by 5, -3 by 5, so your 0 is at -3 by 5, and you have that pole at -1, -2 and -3. Then from this particular expression you can see that if you just plot this gt, if you plot gt versus t, gt versus t, then when t tends to infinity, then obviously all of them will be going to 0, so that means gt would be equal to 0. But here one important thing you can notice, that there are 3 terms, so this term and that term, and here you have that -2, and here you have -3, and here you have -1. So those values, those terms will be dying out very quickly compared to the first term. As this is -2 and this is -3, when time progresses you can see that these particular terms, second and third terms, will be dying out very quickly. So this term will be dying out later compared to second and third terms. So that means if you look at the transient response for this gt, so in the transient response, this particular term and this term is associated with the pole -1. So this term has that more effect, or the effect for this particular term is prominent in the transient response. So that's why the -1 pole, the pole -1 is the dominating pole. Again I am repeating this one. So if you look at that GT, so there in that particular response you will see that the second and third terms, e to the power -2t and e to the power -3t, so these two terms are associated with the poles -2 and -3. So as -2 and say 2 and 3, they are greater than 1. So then the second and third terms will be dying out quickly compared to the first term. In other way, you can say that in the transient response, this first term, the effect of this first term is more prominent compared to the second and third term. And the first term is associated with the pole -1. That's why in this particular function, there are three poles, -1, -2 and -3. So -1 pole is the dominating pole. Or you can say that the pole which is closer to the origin. So this pole is actually the closer to the origin. So closer to the origin. So the pole which is closer to the origin, that pole is called the dominating pole. So the next part, in the next part, I will be showing you some more applications of inverse Laplace transform, and we will be solving some more problems.